Hello everyone, welcome to Geoscience Engineering. In this video, I will be explaining you about a particular landslide and the process involved in processing the Sentinel imagery for detection of landslides, and I will also explain you about each and every step involved, starting from why we need the SLC images, not the GRD format, and what are the steps involved, what do you mean by top star split, what do you mean by apply orbit, what do you mean by back geocoding, what is it meant by ESD, and everything I will explain you in detail. So let us get into the video. Right now I am showing you a place in Nagaland. It's in this is located in Kohima near to Kisama Heritage Village. So this particular area has a landslide between April 2025 and June 2025. So first we will see the coordinates of this place. This is 25.62 and 94.11. So I opened the Copernicus website and downloaded two images. One is of April 22 and the other is May 28 of year 2025. So if we go for the properties, you can see the abstracted data. This is SLC type, the product type is SLC, and this is descending. And then if we go for the second image, the abstracted data. So this is descending, this has a VH vertical, horizontal and vertical. The same way this second image also, it is a SLC product, and then this is also descending and it has a vertical, horizontal and vertical. So first we will discuss why we are taking the SLC image, single look complex images, why not GRD. Landslides, when it comes to the landslides, they are not just a sudden event. In many cases the ground starts moving very slowly, sometimes just like few millimeters or centimeters per year before there is a failure. To detect this slow movement, we are using the SAR interferometry, or we can call it as INSAR, which measures ground deformation using phase information from the radar signals. So the key requirement here is the phase. So when it comes to the SLC, the Sentinel-1 single look complex images, they store the amplitude which tells us how strong the radar signal is, and the phase which tells us the precise position of the ground. So this phase information allows us to create interferograms, calculate coherence, measure surface deformation, monitor slow moving landslides. That is why SLC is essential for landslide monitoring and also for the deformation analysis. So in this particular area, around 10 years ago there is a landslide. After that again, after 10 years this landslide started. So this may not be a sudden event, it might be taking place from a very long time, but because of the monsoon and the favorable conditions, the landslide has occurred this 2025. When it comes to the GRD format, that means the other format of SLC, GRD products only contain the amplitude information. So during the GRD, when we are processing that, the phase will be removed. This means we cannot create interferograms, we cannot measure deformation, we cannot calculate the coherence also. So GRD data cannot be used for the INSAR based landslide analysis. Now when we are going for river or flood analysis, we can use the GRD format. Now let us get deep into the process of analysis. Now there are few methods to process this. So first of all, I will let you show you one more thing, that is, in this you have different bands IW1, IW2 and IW3. So if I zoom out here, my area of study belongs to IW2 and it is somewhere here. So I will show you now say example, if you go to IWT and if you go to the intensity. Now, when you see a single image of Sentinel 1, you have bands like IW1, IW2, IW3, and this has again the intensities. So, we will discuss what are these bands IW1, IW2, IW3, and then we will go into the processing. So, Sentinel 1 mainly operates with interferometric wide swath mode, that means in simply we call it as IW mode. So, this IW mode is designed to cover large areas, maintain a good spatial resolution, and also support the INSAR applications, particularly landslide monitoring or earthquake deformation or subsidence. But the processing depends. When you are going for time series analysis, you will be going for a different set of software like stamps or MintPy, and for DINSAR you will be taking only 2 images like that. Now, when it comes to the bands IW1, IW2 and IW3, IW1 is a near range, that means it is closest to the satellite, and then IW2 is the middle swath and IW3 is the far range, that is farthest from the satellite. Each subswath will be covering a different portion of the ground, that means when you take like this, so this is covering the other part of the ground, this is covering other part of the ground, and this is covering other part of the ground. This is all a single set, but you have different bands again. So, each subswath IW1, IW2, IW3, they will be covering different portions of the ground, and total it will be like approximately 250 kilometers of area. So, this whole area is 250 kilometers. Right now, when you go for the bands, my study area is here at IW2. In this particular area my study area is located, and then in this you will have different bursts also. So, like it says 1, 2, 3, 4, 5, 6, 7, 8, 9. So, these are the 9 bursts in this particular IW2 again. So, that means there are 9 slices. So, when you are processing this particular set of image, the band, it contains a huge area. So, I wanted to minimize the area and I want to focus only on the location where my study area is there. So, I will go for the subset, or I will go for the split, I will go for topser split, in which I will remove all these unwanted areas and I will only focus on my area of investigation. I will also tell you why we are doing this one. This is because when you are going for applying orbit or doing any kind of interferogram generation, the larger array will take more space, more time and more data. So, when you make your area of investigation focused and you cut the whole remaining area out, and like you remove the remaining part of this area, then your processing will be fast, your result will be accurate, and your data will be easy, and then you have very less time for the processing. Now, I will tell you what are these subswaths. A subswath is called as a burst. It is actually a small block of data. This is one block of data 1, 2, 3, 4, 5, 6, 7, 8, 9. So, there are 9 blocks in IW2 burst, IW2 swath. In the same way, in IW1 there will be 9, in IW3 there will be 9. Okay. So, now we are going to in deep detail about the landslide investigation of Kohima. In this, the bursts, they are we are using for IW2, and then we are taking the same burst for the second also. That means, when you are taking 2 images, they should have the same subswath and they should have the same burst. Now, to simplify this process, we have one option called Sentinel tops co-registration with ESD. There is one more thing, if you want to see this graph, see, when you open this graph, there are different steps involved, it is like a complete package. So, So, read 1, read 2, tops are split, apply orbit, back geocoding, ESD and write. If you want or if you have more storage, you can directly go to Sentinel 1 top split and then go for the split and then apply orbit, and then you can go for the co-registration, and then you can go for back geocoding ESD, but this will take a lot of time. So, we will directly go for the single process which involves processing of everything at a time. So, first we need to take the first image, that means before the event, as read 1, that means that will be a master, and then second will be the slave. So, the first image I am taking it is on April 22nd 2025, and the second image is after the landslide, that is 28th May. Now, I am clear up to this part. Now, I will discuss about the tops are split. So, right, like I told you, tops are split is like you are splitting the whole area, your required area from the whole area. So, IW2 is my area of investigation. So, I can zoom and see like this, and if you see here, my area of investigation is around here. How to identify? You can see the latitude longitudes here. So, my area comes under 26 point like this, it is 25.62 and 94.11. So, we can take an approximate area like this 25 point. So, at particular this location you can find it. So, what I am doing is I am just keeping this 1, 2 and 3, and then I am removing the remaining parts. So, for that what you can do is you can slide this, then maximum burst. So, when I am reducing the number, you can see here the bursts are reducing. So, I will take only 1, 2 and 3. So, the smaller the burst, it will be good for you to do the processing. So, I am taking 1, 2, 3 here, and then that is from 7 to 9, the last 3 I selected, and remember the same split you should do it for the second image also. Again we have to go for 7 to 9. Okay. So, if I am clear like this 1, 2, 3, and we have 789 IW2 and 789 IW2. This is much important. Now, I will tell you what is about applying the orbit file. So, when we are processing the Sentinel images, we should first look for the first step of applying the orbit file. So, when we are processing the Sentinel-1 data in ESA SNAP, one of the first thing you see is apply orbit. That means, but what does this actually mean, and why is it so important for landslide and also for displacement analysis in the INSAR studies. So, when every Sentinel-1 image contains information about where the satellite was in the space when it is recording or the data is captured. However, this position is not perfectly accurate in the original product. So, the apply orbit file will replace the rough satellite position with more accurate orbit trajectory provided by the ESA. In simple terms, we are actually correcting the satellite path so that the image is placed in the right location. For normal image viewing or small orbit errors, it does not matter much, but for INSAR, especially for subsidence or landslide deformation analysis, they are very much important. Accurate orbit information is needed because precise correlation between two images is important, correct information interferogram formation is important, reliable phase difference calculation is important, and also to avoid artificial phase ramps and errors. That means, even a few centimeter difference of the orbit, it will completely ruin the processing or completely ruin the interferogram. So, in this step, if you are skipping this particular part, the images may not be properly aligned or the interferograms may show strong ramps. Deformation results also may be unreliable or may be completely wrong. So, when you have the orbit state vectors, as we are processing the Sentinel one, we will only discuss about these two, Sentinel precise and Sentinel restituted. These are all for the other satellites. Now, we are only discussing about Sentinel. So, we have to choose either this one or this one. And when it comes to the restituted, Sentinel restituted, it is available within a few hours after the acquisition. It is moderately accurate and suitable for quick processing or emergency responses. Restituted orbits are automatically included in many Sentinel-1 products, but when it comes to the Sentinel precise, this is more, the name it suggests precise, that means it is available after several days later, but this is more accurate and it is computed using the ground tracking satellites and refined models. For scientific studies like landslide deformation, long term monitoring or time series INSAR studies for subsidence, precise orbits are strongly recommended. So, I am selecting the precise auto download, and they do not fail if the new orbit file is not found, because sometimes the data acquisition and after several days this precise orbit will be found, I mean it will be available. So, if the latest is not available, it can also go for the previous one. So, that is why we are keeping it as do not fail the orbit if is not found, and for the same second Sentinel precise. So, I am clear with the SLC image, and then why we are choosing the SLC image, what are the bands IW1, IW2, IW3, and then we have discussed about the burst, and now we have discussed about the master read 1 and read 2, and the importance of topstar split and the importance of apply orbit. Now, we will go for the back geocoding. In this you have a digital elevation model, resampling method and resampling type. So, in this we are adding a digital elevation model to our satellite image. So, here you see the digital elevation model and DEM resampling method and resampling type. So, here we will discuss about the geocoding first. During the Sentinel 1 for INSAR processing, the key step is back geocoding. This step is also asked for DEM or DEM resampling methods and also for the resampling type. So, back geocoding is precisely aligning the pixels by pixel according to the master and the slave, and they are both aligned to or aligned with the digital elevation model. In SAR images, data is originally from the radar geometry, that means it is like a slant range. Terrain height causes geometric distortions also. So, when we are using the back geocoding, it contains orbit information and also digital elevation model. These are used to correct the distortions and align the master and slave images accurately. So, back geocoding makes sure both images look on the same ground point from the space. And why do we need a digital elevation model? A DEM represents the elevation of the earth surface. SAR images are affected by terrain effects such as foreshortening, layover or shadow. When you do not have a digital elevation model, SNAP cannot correctly project the radar pixels to the ground coordinates. Correlation will be inaccurate. Interferograms may also contain phase errors. This is especially critical in mountainous landslide areas like the one which we are doing now. So, where the elevation changes are very large. So, that is why we need a digital elevation model. In this digital elevation model, you have SRTM 1 sec, SRTM grid, SRTM 1 sec HGT, SRTM 3 seconds or external DEM. So, if you have anything like external digital elevation model, you can use that. Now, I will explain you about these three. SRTM 1 sec is 30 meter accuracy, which is most commonly used because this has a global coverage and this is good balance with resolution and reliability, and it is suitable for most landslides and INSAR studies. When it comes to the 3 sec, this is 90 meter resolution. So, this is little low in resolution and this is less accurate also, because we are doing it in a steep terrains, and this is only for large scale or flat areas. When you go for the others, the Copernicus 30 meters or 90 meter, this is having high accuracy than SRT, but better terrain representation. This is also recommended for mountainous landslide zones, and external dams are from LIDAR or any other national dam, you can use it. So, right now we are using SRTM 1sec HGT, okay. And after that there is a process called dam resampling method. Why do we need a dam resampling? Dam resampling means we are adjusting the digital elevation model grid so that it matches the pixel spacing, the geometry of the SAR image, and because digital elevation model and SAR images usually have different resolutions, different coordinate system. So, SNAP must resample the dam before using it, and in the resampling types you see bilinear interpolation, cubic convolution, like this. Here also you can see the same. So, I will tell you in both of the columns, I will tell you the nearest neighbor is fast, it keeps the original elevation values, it can create blocky terrains, but this is not ideal for the INSAR. When it comes to the bilinear interpolation, it is mostly and widely used. This uses the surrounding pixels, it will smoothen the elevation transitions, it is having a good balance for speed and accuracy. And when it comes to the bicubic interpolation, it uses more neighboring pixels, and it has a smoother terrain, it is slightly slow, but it is good for high resolution digital elevation models. Now, in this we will be selecting only the bilinear interpolation, this one, and here also the same, and then we will go to the next step of enhanced spectral diversity. Okay. Next, yeah, here we are here with the enhanced spectral diversity. So, we will discuss about this one also now. So, during the Sentinel 1 tops, the radar beam, it rotates during the acquisition and records data in bursts, and each burst has a slightly different Doppler frequency. Because of this, even a tiny misalignment that causes between the or a slightly misalignment that occurs between the bursts, and this will cause effect to the loss of coherence. So, that is why we are going for the enhanced spectral diversity or ESD. This is for the co-registration. This is used for overlapping areas between adjacent bursts and the Doppler frequency differences to measure and to correct very small azimuth shifts between the master and the slave images. In simple, ESD will fix tiny burst to burst alignments or misalignments that normally co-registration cannot detect. That is why we are going for the ESD. In this ESD, in Sentinel 1, the phase accuracy must be extremely high. Even the millimeter level of motion matters a lot, because when you go for a subsidence study like time series, a millimeter change difference can impact a lot. And when you are not using this ESD, you may see some phase ramps or burst boundaries may be visible, like the lines will be visible, and the interferometers may not be that good and they may contain lot of noise. When you are using this ESD, the burst alignment will be a single piece, like you do not find any kind of breaks, and the phase continuity will be preserved and the coherence will be improved. That is why ESD is mandatory when we are going for the TOPS or Sentinel 1 data. Now, we will keep this as it is, and then we will go for the write. This is the last step. So, you can select the folder and then click run here and let the processing complete. So, this will download the orbit required for the apply orbit, and it will also create the split, and then it will do the back geocoding, and then it will do the ESD, and then it will finally give you the output. So, here when I click here, and these are the two images now. See, all you can see is a big piece of all the three swatch IW2, IW1, IW2, IW3. Once the required path is processed, you can see a highlighted area here, then you can close all these three and then you can focus only on the study area. So, we are completed with the process, and then you can see out of the whole images my area of interest is open. So, I am closing the two images so that it will be clear. You can just click yes. So, from the whole area, now my specific area of interest is cropped. Now, we have the final image with ESD. This is intensity IW2 vertical to vertical master, and this is for the slave. Now, you can see little differences here in this. Once this completely processed, then we can see the final image. Now, why we are only focusing on the intensity and that too VV. So, we will discuss about that one. When in a Sentinel-1 radar images, VV means vertical transmit and vertical receive. So, in VV polarization, the radar will be sending a vertically polarized signal and it receives a vertically polarized signal back. This is one of the most commonly used polarization in Sentinel-1, and when we are focusing about the intensity, this means this has amplitude and phase, and intensity is derived from amplitude. So, the value of intensity depends, VV will depend mostly on the surface roughness, soil moisture, vegetation structure, building orientation and slope related to the radar. When the intensity is low, you can see dark areas for the smooth surfaces mostly. During the rough or urban spaces, the intensity is high, that shows the bright images. So, bright areas means it is a strong backscatter, and dark areas means it is a weak backscatter. This makes intensity images for land cover mapping, landslide scar detection and change detection after the events like earthquakes. Now, we will move forward to the next steps. I can show you one more clear picture using the RGB window. So, this will make you understand clearly. So, right now you can use this master VV and slave. So, for the red I am using the vertical master, and for the green I am using the slave, and then you can click OK. See, this is somewhat better when it comes to the previous black and white image. Now, we will just zoom in a little and see the differences. Now, we will go for the next important step, that is interferogram formation. So, we will directly go for the interferometric and product, and then we will go for the interferogram formation. So, in this we have different options again, but first I will explain you what is interferogram formation, and then we will go for the what is subtract flat earth phase, and then why we are not selecting the subtract topographic phase, and then for the coherence what is output coherence, and then what is square pixel also. So, when we are going for the interferogram first, an interferogram is created by two images, that is the master and the slave, and comparing their phase values pixel by pixel. This is mathematically we are creating one image. So, the result in the new image, it is showing each pixel represents a phase difference, and that phase difference contains information about the ground deformation, topography, orbit geometry, noise and atmosphere. So, even if the ground did not move, the interferogram would still should contain the phase. This is because Earth is curved, the satellite move along a orbit, the distance from the satellite to the ground will change across the image. This produces a large and smooth phase patterns called as flat earth phase. So, we are subtracting the flat earth phase to remove the orbit related geometry effects and deformation, and the topography will be hidden. So, we subtract the flat earth phase. This is also because to remove any kind of orbit related geometry effects and make the real signals visible. This step does not remove deformation and topography, it will only remove the geometric trend. And then when we go for the coherence measures like this, first I will also explain about why subtract the topographic phase. We are not selecting it because topographic phase is caused by elevation difference on the ground. To remove it, we need the diselevation model, which is a again we will do in a separate step called as the topographic phase removal. In that we do that, but during the interferogram formation we usually only subtract the flat earth phases. This keeps the topographic phase intentionally because some workflows need topography for the later stages also. So, that is why we are not removing the topographic phase now. And then when it comes to the coherence, coherence measures how similar the two radar signals are. It will tell us about how reliable the interferometric phase is, whether deformation estimates can be trusted, and the coherence values will usually range from 0, that means no correlation, which is noise, and then 1 is perfect correlation. Low coherence generally caused by vegetation, snow, landslide movement or temporal changes. Including coherence will help us in the reason why we are selecting this, enabling this is because it makes it helps in masking unreliable areas, it helps in interpreting the interferogram correctly, and it helps in identifying the active landslide zones. So, I have selected the subtract flat earth phase and then coherence, and I am keeping the values like that and then just run. So, this may take some time, then we will be going for the next further steps. Okay, done. Now, if you see here in the intensity, and then we go for the phase, and then we go for the coherence. Okay. So, if you zoom to a particular area, you can see some differences here, the ground. So, I will show you everything clearly. Now, we are going for the next step called deburst. So, we will go to the Sentinel tops and Sentinel top deburst, and then you select the VV because we are using the polarization VV, and then we will go for the run. So, here is the debursted image and here is the previous image. So, you can see some correction here. So, I will tell you why we have to go for the deburst. Sentinel 1 operates in IW mode using the TOPS acquisition. In this mode, the satellite does not record one continuous image. So, it has subswaths like IW1, IW2 and IW3, and the bursts are slightly overlap with each other. This allows wide coverage, but creates visible burst boundaries in the data. This is like the visible burst boundary, and when we do the deburst, the boundary is removed. So, the topside deburst is used for removing the overlapping burst edges and merging the individual bursts, creating one continuous seamless image for each subswath. So, it is something like deburst means stitching all the small burst pieces into a single clean image. Okay. And when you are not using this one, the burst boundaries will remain visible. So, this boundary is still visible because I did not do the deburst. After the deburst, that boundary is removed. When you do this, the phase becomes continuous, the interferogram will become smooth, the coherence will also improve, and the deformation results are also visible. Now, we will go for the most important step now. We are going for the topographic phase removal, interferometric products. Here, we will discuss about the topographic phase removal also. So, in an interferogram, the phase differences comes from several sources: the ground deformation, the satellite geometry, atmosphere, terrain height, or the topography. The part of phase caused by elevation difference is also called as a topographic phase. So, mountains, hills and valleys create phase fringes even if the ground has not moved at all. So, high terrain means more phase changes, low terrain means less phase changes. So, for a landslide and a deformation studies like subsidence, we are interested in surface movement and not in the elevation. So, if the topographic phase is not removed, interferograms are dominated by the terrain fringes and the deformation signals will be hidden and the phase unwrapping becomes difficult. So, topographic phase must be removed to isolate the true ground movement. As in the previous step we added this SRTM 1sec SGT, now we are removing that part. Topographic phase removal generally means using a DEM, simulating the phase caused by the terrain and then subtracting this stimulated phase from the interferogram. After removal, the remaining phase mainly contains ground deformation, atmospheric effects and noise. Now, we can click on this on the elevation band and then you can click run. Now, we will go for the next step of multi-looking. Now, I will tell you why we need multi-looking also. Okay. Here you see going for the process of multi-looking. Here SAR images generally contain speckle noise, that means they are caused by coherent interference of radar waves, the rough surfaces, multi scatters in a single radar pixel. So, multi-looking means averaging several neighboring pixels in range and azimuth direction to reduce the speckle noise. So, in simple words, we are smoothening the image, reducing the noise and also improving the interpretability. So, here the number of range looks are 4 and then we are just leaving it like that. We have the source bands from the previous image, we have the elevation, we have the topo phase also. So, let us have a look at that one once. We have the topo phase here and then we have the coherence image and then we have the phase also. Now, we will apply the multi-looking and then see the result. Once this is done, we will go for the next phase of Goldstein phase filtering here and then we select this image and then we go for run. So, I will tell you why we need Goldstein phase filtering. This means even after multi-looking, interferograms may contain some more phase noises. This is due to the residual speckle, atmospheric effect or small uncontrolled signals. This noisy phase will make the interferogram fringes hard for the interpretation and then the coherence will be unreliable, the phase unwrapping process will be unstable. So, the phase filtering is used to smoothen the phase while we are preserving the real signals. In the Goldstein phase filtering, we are working with the frequency domain. The interferogram is converted into Fourier space and then the filter suppresses high frequency noise. It keeps low frequency signals which corresponds to the real deformation or topography. So, it works well with moderate or low coherence areas. It also preserves the fringe patterns. It is compatible with any of the SNAP workflows. So, before filtering, interferogram looks noisy and messy. The phase fringes are also hard to see. If you want, I can just show you. So, here in the bands, the topo phase, sorry, the intensity and the phase, see they are a little different, but once we go for this phase filtering, we can see a lot of changes. After Goldstein phase filtering, we can see the noise is reduced, the fringes are clear, and the phase continuity will be improved. So, we can just have these values. So, I have applied the Goldstein phase filtering here, and then you see this is the before Goldstein phase filtering and this is after. So, you can clearly see that the noise has been removed and few areas are highlighted. Okay. So, next we will go for the steps of final processing. Now, we will close everything and then we will go for the next steps also. So, this is the coherence image before and this is the intensity image before and intensity after. Next we are going for other corrections like range Doppler terrain correction. So, we go for the interferometric and then we go for geometric terrain correction, range Doppler terrain correction. So, here if you can see the interferograms, intensity, phase, topo phase, coherence, elevation are all loaded, and the digital elevation model which you have selected is 1sec HGT. And now I will tell you why we need the range Doppler terrain correction. So, our images are generally acquired in the slant range geometry, pixels representing the distance from the satellite to the ground along the radar line of sight, and terrain slopes and mountains cause this geometric distortion like foreshortening, layover and shadows. This means the image is not directly aligned with the latitude longitude coordinates. For landscape mapping or any kind of GIS analysis, we need the image to be in a map geometry. That is what the terrain correction will do. So, here you see this is having the map projection, the pixel spacing, and about the latitude, longitude, output bands and all these things. So, here what we can do is we can select the okay. So, let me also tell you one more thing. Range Doppler terrain correction uses satellite orbit information, the radar equation geometry and a digital elevation model. The digital elevation model which we have used is 1sec HGT. So, it converts the picture from a slant range geometry to map projected coordinates. That means, it will flatten the image and places it exactly on the ground. So, once you import the image into the Google Earth or QGIS, the image will be exactly aligned to the map projection. Without the range Doppler terrain correction, the interferogram or the SLC images may not be aligned along with the map or with the shape files, and the pixel spacing will be uneven, and the deformation measurements also inaccurate, and the GIS overlays are also not possible, because when you are trying to overlay, the image will be placed on some other location. So, for this the range Doppler terrain correction is very much important. Each pixel is corrected according to the geolocation, and the interferograms and the intensity images can be used for both mapping analysis. Now, we will start the process. So, after the range Doppler terrain correction, you can see the image is aligned according to the coordinate system. See, this red boundary is generally the image. Now, it got aligned exactly to the projection system. Now, we can go for the next step, that is subset, because the big area it is difficult for us to project on the Google Earth. So, we can just go for the subset and then we can take only a part of it and then we can use it. Here you have the subset option. here it will be in the raster and then go for the subset. See, here you can see a bigger area. Now I don't want the whole area to be covered, so I can just, if you know the area, then it would be easy for you to define it. So you can just zoom in with select with your cursor, or if you know the coordinates, it would be more easier for you to understand, and add. So when you are doing this one, you can see the size also. The size will also decrease. See, it's 170 MB like this. So you can just use that, or you can drag it like this. Right now I'm just keeping it here, and if you have the coordinates, you can use that, or you can just use a normal way of manually pulling the area. I am just taking the reference like this image here, and then I am doing the subset, and then I click OK. So see, now out of the big image, I even got my small image here like this. Okay, so if you see the output again for the face, see now it is divided from the whole area, it got separated, and this is my area of interest now. Now we will go for the next step. So finally we got the image. Now we select it, and then we go for the file, and then we can export other, and then go for the KMZ format, and then you can save it. So I open this interferogramic image in the Google Earth. So now you can see this interferogram, the phase image is exactly on the location now, and see this place. You can see the phase values here, and this phase contains the terrain height causing the phase differences, deformation, that means the ground movement between the acquisition from the master to the slave, and the satellite geometry. This also shows the fringes, and now we are discussing about the values also. From here you have 2.46 and minus 2.44. So the values are phase difference in radians, and positive values means, the positive values means the radar path increased from the master to the slave. Negative values means the radar path decreased from master to the slave. So the positive values generally indicate that ground has moved away from the satellite, and negative means the ground has moved towards the satellite. Whether the displacement is towards or away from the satellite depends on the slope orientation related to the satellite look direction. If the slope is facing the satellite, like downward movement, landslide will move towards the satellite in the negative phase. If the slope is away from the satellite, downslope movement may move away from the satellite, which means a positive phases. We cannot directly say that positive is a landslide or negative is not a landslide without knowing, but we need to consider the satellite look direction and the slope orientation of the terrain also. So I just took an example of this, and then explained you every step involved in the processing. If you have any other queries, you please let me know. I can explain you in the comments, and thank you very much. Please do subscribe and like the video. Thank you.